All right, recording is rolling. So it is Tuesday, November 15th. I'll give you guys time in class today to work on chapter 6 puzzles and teams. I'll walk around, help you guys out. This will be anything on your part. I don't know if you guys have time to finish all of them in class, but it's going to be kind of a fast-paced week. It's going to be probably a bit more homework on you guys than normal, just because we missed it 2 days last week, but trying to make this happen. Okay. You guys do have those solutions on your desk, but like I've told you guys multiple times in the past, try to do the problems from scratch yourself, just from a blank piece of paper. And if you're like really stuck, you thought really hard, then you can go back to the solutions and see like at least one way to get this to the answer. Right, for each one. Right, I can help you guys out too. AP Classroom videos. I know I've mentioned these a few times in the past, and I think I showed you guys a couple. Studio was telling me that these, like for this section, they're particularly helpful. I guess like from her perspective, so take her advice. Because different sections, I guess, are presented differently and have different presenters. So if you want a little bit extra resource, then that might be a good thing to look at. So reminder, you guys know there's an in-class quiz on Thursday, a few days from now. It's going to be open notes, so any notes you took last week, yesterday, today, tomorrow, you bring in. So I posted class grades. This is bar chart of what they look like. I just see some of you guys have just turned in some assignments, and the window's still open to post stuff. So I will try to get those in. Anything that you just turned in now. I do have a starter question for you guys that it didn't exactly 100% cover, but it's also very similar to one of your book questions. Right. And I could see AP asking this question too. So here we go. Suppose you have a ball that's like this many kilograms. By the way, that's like about the mass of a baseball. So imagine you take a baseball and you chuck it against the wall. Right? And we're looking aerial views. So I'm looking from above and looking down. And the only reason I'm doing that is to simplify this a little bit, just so that weight is not a factor, right? Like weight is like so we're ignoring the weight of the ball, right? This bouncing off it's all like lateral motion that I care about, right? And so ball boing bounces off the wall. And the time of collision is, of course, it's a tiny fraction of a second that the ball is actually in contact with the ball, right? Okay. And the question is, what is the average force on the ball from the wall to the left? Okay, what's the average force? Okay. I gave you guys some numbers. Here's the speed of the ball. I did tell you guys it was an elastic collision, so the speed stays the same, right? And I gave you guys some angles there. Right. Now, I know I think Talia and friends back there already solved this and got it right, but everybody else, here, I'll give you guys about a minute here, see if you guys can figure this out. I'll say show of hands, give you guys multiple choice options. You can figure this out. What is the force on the ball from the wall? Or if you like, what is the force from the ball back on the wall? Because Newton's third law of motion would be an equal and opposite force. Give you guys a hint while you're thinking about it. The force from the wall, that would be a what kind of force starts with an N? No. Normal force, right? Is normal force. Normal means perpendicular, right? Right. So which direction is the force from the wall on the ball? It's to the left, to the left. It's only to the left, right? Right. Is there any force that goes like parallel to the wall? I don't think so. Well, I mean, maybe friction could like cause a spin on the ball, but let's ignore friction. Don't care about friction. Right. So I only care about the normal force. The normal force. All right, a few more seconds. All right, let's go through I want to say show hands, show hands. So you guys see these multiple choice options, right? It's one of those. So show hands. How many of you guys got 8 newtons? Who got 8 newtons? Right. So got a few votes on that. Who got 16 newtons? 16. Okay. Good. So some votes on 16. Who got 24 newtons? 24 newtons. Oh, nobody got 24 newtons. Well, that's good because it's not 24. Who got 32? 32 newtons. All right. Winner, winner, winner. All right. There's my winners right there. 32 newtons. Hey, how'd you guys get 32 newtons? Yeah.
The change in velocity over change in time multiplied by the mass. So 16
All right.
divided by 0.075 gives roughly 213 and a third. And you multiply it by the 0.15 kilogram ball for the mass times acceleration to get 32.
All right. That sounds good. That sounds good. All right. I think this is going to back up what you're saying too, right? So here's some recent tight notes you guys saw. There's some kind of impulse going on, like a change in momentum of the ball, because there's a change in direction. Now, the speed of the ball doesn't change, but the direction changes. So there's like some force, some change in velocity of the ball. In the ball has some mass, so there's some impulse involved, right? Right. So here's one way to think about impulse, right? Mass times change in velocity is average force times the time interval, right? If I swap both sides, just switch to the left or the right, it looks more like this. And I did that because then if you divide the delta t over, right, hey, doesn't that look like Newton's second law of motion? Remember, impulse and Newton's second law of motion are just one step away from each other, right? They're almost saying the same thing, okay? Okay, so, right, you have the mass of the ball, check. You know the time interval of collision, check. So let's just pop it in, pop it in. Okay. Now the delta V, now here's where you need to do a little bit of trigonometry, okay? Because the fact that the force from the ball was only to the left, right? Right. And see, the motion of the ball didn't change at all parallel to the wall, right? See, like if you just watch the ball going parallel to the wall, right? Guys, how fast was it going like strictly up the page? Because total speed was 10 meters per second. Because what's 10 meters per second times cosine of 53 degrees?
6.
Yeah, that would be, yeah, that sounds right. Yeah, 6 meters per second, right? It was going 6 meters per second before, it was going 6 meters per second after. So there was no change in that direction. The change was entirely this way, right? Because how fast was that headed towards the wall?
8 meters per second.
8 meters per second. And how fast away from the wall?
8 meters per second.
8 meters per second in the opposite direction. Guys, what's the difference between 8 one way and 8 the other way? 16. Yeah. So when Elijah was brought out that explanation, he said something about 16 meters per second. So we got that from, right? The difference between positive 8 and negative 8. You guys know the difference between positive 8 and negative 8 is 16 units, right? Right. So if you do 10 times cosine of 37 degrees, or if you do 10 times sine of 53 degrees, either way, you're going to get 8 meters per second towards the ball. And then when it rebounds the boing, it's 8 the other way, right? The difference between 8 and negative 8 is 16, right? Right. So here, let's pop this all in. So the mass of the ball is 0.15 kilograms right there, times a change in velocity of 16 meters per second, because 8 minus negative 8. Here, let me spell that out. 8 minus negative 8, right? And then all divided by the time interval of 0.075 seconds. Yeah, that's going to give you 32 newtons. 32 newtons. Okay. You guys good there? All right. Any questions so far? You know what else I want to do? I did make you guys an addendum video yesterday because I wish I did this, but you guys see these posters hanging from my ceiling, so I'm gonna flash through these real fast. So you guys know momentum is mass times velocity. If you had all the mass velocity bits before the collision, and then after the collision, they have to equate. That's what conservation momentum is. Now that's for a closed system, right? As long as you have a closed system, no external forces going on, right? If these two guys stick together, you can just modify this a little bit. Okay, and then they stick together, make one giant mass move, some common final velocity. Okay. this also works in reverse for like exploding grenades or like throwing a snowball on an icy like frictionless surface, right? Where you start with like you with the snowball and you throw it one way, right? So this could go like forwards of time or backwards of time, but you can do this, right? Right. Where's there more kinetic energy in the top scenario or the bottom scenario? Where's there more kinetic energy? This one right here, right? When two objects collide and stick together, there's always a decrease in kinetic energy. Does that energy disappear from the universe? No, it goes into like a permanent deformation, right? Like imagine like two play balls. Maybe they got a thermal energy change. Like if you measure the temperature, but the temperature goes up. Right? I bet you can hear it like sound energy, like waves. Right? The other extreme kind of collision you can have is perfectly elastic. So it's right here. I think there is a class question on AP Classroom. You guys, that's what else I meant to mention. You guys are going to turn in an AP Classroom before tomorrow, right? Because we're going to go over AP Classroom tomorrow. Okay. So I double checked. There is one question about perfectly elastic. Here, I'm going to tell you guys. I think the best way to solve it is to play off multiple choice. To go through all the multiple choice answers and see like which one checks out with both of these conditions. That's probably the fastest way to solve it, right? I think that's why they made that multiple choice question. Okay. You got, of course, your impulse. Oh, guys, the whole problem we just solved with the ball bouncing off the wall. You guys know we only solved for this type force, right? The average force, right? But if that, and that came out to 32 newtons. Suppose if you put like 50 newtons on the ball, it's gonna like the seams break and it breaks open. So you said, okay, average force was 32 newtons. Is the ball safe or is it gonna break open? I bet it's gonna bust open if if it breaks at 50, because 32 times 2 is that's more than 50, right? Like 64. Okay. Right. So yeah, keep in mind, like all those impulse stuff, you're really solving for average force, right? Right. But more realistically, they tend to look like this. But force versus time, guys. What this was force versus distance? Oh yeah, go ahead.
So will the maximum force always be 2 times the average?
Yeah, that's a pretty typical thing. Yeah, for maximum force to be double the average force. Yeah, especially if it's like straight lines like this, like a nice looking triangle. That'll be the case. Okay. Here, let me throw a couple scenarios at you guys. This really the same scenario, but pitch it you a little bit differently. You use different frameworks. Suppose you have a rocket going in space, deep space. It blasts its rocket engines. Oh, blasting its thrusters. That's like a force, right? Like an external force, right? Pushing the rocket. It's gonna cause it to accelerate, speed up, right? Now, if they tell you that the rocket, that the thrusters go for like 100 meters, so you have a force versus distance graph, which is not exactly what you're looking at. Force versus distance. Then the area under the graph would represent what? Force versus distance. The area represents work, right? Which tells you the rocket's gonna be speeding up, so the work on the rocket would translate to a change in its what? Kinetic energy. Yeah, kinetic energy. You said 1/2 mv squared versus 1/2 mv squared, right? Right. The original versus the final. Something is speeding up. But if they tell you the thrusters blast for like 8 seconds, well, now this is what you're looking at, and the area represents impulse, which is a change in mass times velocity, a change in momentum. Okay. Finally, I do have a poster for a coefficient restitution. I've never seen AP ask a question on this, so good to know about, but don't really study too hard. Okay. You guys good there? All right, so you guys got the rest of class. Work on your college physics puzzles. I will walk around and help you guys out.